So, now actually we will go into parity games, the thing that I was talking to you about. So, once again you see reachability was, I mean always the play is infinite, okay, but the play in the reachability case the play was winning as soon as you hit a good node. Okay. In the repeated reachability, a play was winning if you visited a certain good thing infinitely often, right. So, somehow we want to develop this idea in a hierarchical manner. Okay. So, this leads us to this main model of games called parity games. So, here once again you are given a game graph as usual, but now these are not the names of vertices, because you see there are 2 vertices with 4. So, these are not names, but we are going to add a specific color to each vertex. Okay. So, there are a bunch, you can call it color, priority, rank, whatever you want. So, for each vertex we add a number. Okay.
Not only color but priority also.
I mean no, the name, I mean some people call it priority, some people call it color, some people call it rank.
Like the square with 1 and square with 4, there is no priority in that, right? They are just different colors.
Yes. Okay. So, now what I want to say is that suppose I look at an infinite play. Okay. So, for instance let us say 4 3 4 3 4 and so on. Okay. If I do this, let me just write down the numbers, write down the colors. So, the colors will be 4 3 4 3 4 3 4 3 and so on. So, I will look at the set of numbers which occur infinitely often. Which of them are occurring infinitely often here? Both 4 and 3 are occurring infinitely often. Among them, which one of them is the greatest? 4. This number is even. Okay. So, player 0 wins. Okay, that is the parity here. Okay. It is one weird definition if you just see it like this. Okay. But so, we are looking at an infinite play, we are looking at the colors, and we look at the set of colors that occur infinitely often, look at the maximum among them. If that is even, player 0 wins, if that is odd, player 1 wins. Okay. So, it is some kind of a hierarchical game, we will get used to this in some time.
How do you say that it's even or odd? It is an infinite game, right?
4 even.
Sorry, come again. No. So, you just assume that you are given a play. Okay. You look at the things which come, no, it is not the number.
Yeah,
It's
see,
the
number of times it comes. Like it is an infinite game, right?
no, wait.
Number being the 4, right?
Wait. See, suppose I write this 4 3 4 3 4 3 4 3 and so on. Okay. What are the, I mean here 4 occurs infinitely often. Let me tell you, 4 occurs infinitely often here, 3 occurs infinitely often. Suppose I tell you this, and among this 4 is the maximum. So, I will just say 4. So, the value of that play is 4. Okay. And if this is an even number, player 0 wins. Whereas, if I had something like suppose this thing 2 3 2 3 2 3 and so on. Okay. Here what is the maximum, what is the maximum number which occurs infinitely often? 3. That play will be winning for odd,
So
for player 1.
targets are even number for 0 and odd for.
Yes. Yeah. Okay. So, it is a little bit of a kind of a, I mean we will look at algorithms for this, and then you will understand what is the hierarchical thing going on inside, okay, in some sense. And as I said, these games come from logic and automata, where there are all these alternations, there exists for all, there exists for all and so on, and they lead to this kind of ranking system. Okay. So, can we think of, maybe I will just start let us say, let us start with a simple, suppose my game starts here at this vertex. Okay. How should the players play? Well, I mean, yeah, from here, okay, but then let us carry on from there. Like, so suppose I start from here, okay, the token will move here. Now 0 has 2 choices. Okay. What will 0 do?
Doesn't matter, right? Yeah. Can give to anyone.
But then that depends on the. It's always better to.
Yes, so
It
suppose,
will go to front. I mean, it will
which 4? It goes into the left 4 or the right 4?
But even if it goes like the sequence will remain the same.
Okay, wait. Suppose it goes to the right 4. Okay. But here, it depends on what will this player 1 do. Player 1 will drop it here. Okay. Now, suppose player 0 comes to 3. Okay. Suppose player 0 does this. Then, this is the suffix of the play which keeps happening 2 3 2 3 2 3 2 3 and so on. Okay. And what is the, see all this initial prefix, they came only finitely many times. This loop is iterated infinitely often and the priorities there are 2 and 3 and the max priority there is 3 which is odd, 1 will win. Okay. So, it is not good for 3 to play this, it has to go to the left 4, because if it does that, then the play will just be 3 4 3 4 3 4 3 4 and the maximum priority is even, which is good for player 0.
Why is the max priority between 2 and 3 of 3?
See 2 and 3, what is the max?
Like we start the sequence will start with 2 first. Right?
Yes,
2 3 2 3.
yes. Just look at the number which is bigger, do not look at the count.
Oh, okay, okay.
Okay. So, the number which is bigger is 3 and that is odd.
But how are we assigning the priorities to different?
This is given to us, you are given this game graph, okay, and then you are asked for computing a winning strategy in this sort of a, okay. Let me continue so clearly here come here, but 0 should not be, I do not know what happens if 0 plays this. Suppose 0 plays this, goes here, okay. This is under 1's control, okay. If 1 plays this edge, then you have this loop 1 2 1 2 1 2 1 2 and the max is 2, which is bad for player 1, okay. So, 1 will push the game here, so that finally you end up in this loop if 0 plays here, and if 0 plays here 1 can force to end in this loop, okay. And both these loops are odd 3 and 3. So, all these are winning for player 1, this is winning for player 1, player 1. Come again?
So it wouldn't, 0 wouldn't want it to go down. So it would just choose the left one instead of
Yes, 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 exactly. Okay. So, now you see the algorithm to compute winning regions for this kind of a game has been open for a long time, as an open in the sense finding an efficient algorithm. You understand the game now, right? And then we want to compute winning regions, okay. And what we will do is we will look at some exponential time algorithms just to understand what is going on, okay. And I do not know if there will be time, if possible we will look at one quasi polynomial time algorithm, okay. Fine. So, here is a question, without answering loud, can you try to think about it? So, there is this Bucci condition, which is in any play a bunch of vertices, they have to come infinitely often. Can I see it as a parity objective? How do I assign priorities so that if I win the parity game, if player 0 wins the parity game, rather player 1 wins the parity game, if and only if player 1 wins the Bucci objective. You see what I mean? Yeah.
The targets should be odd numbers for player 1 and even for player.
Bigger odd.
Bigger odd number, correct, yes. So, you are right. So, the target should be 1, let us say call it 1, and if we allowed 0, then you can put even numbers to be, the others to be 0. But I do not since we are, I think we start with 1, so in which case put 3, others you put 2, okay, you are right. So, if in an infinite play, if the max priority that comes infinitely often is odd, it means that you have visited the target vertices infinitely often, okay. So, you see that the Bucci condition is like at a very low level of this parity. It's like there are many more indices in this parity condition. Okay, so it's that is the one that makes it difficult.
So what was the time complexity of the previous algorithm?
It was n times m.
Oh, right.
Yeah.
Could you repeat the last part?
Yes.
The Bushi condition.
Okay. See, what I am saying is, suppose I look at a play. So I have this graph, and for all the t vertices I have put 3, and for all the other vertices I have colored them with value 2. Okay. Now suppose I look at an infinite play, which is winning for player 1. What does it mean? It means that 3 occurs infinitely often. Right? That is the only way it can win for player 1, right? Because 2 and 3 are the only indices. There is no 4, no 5, anything. Only 2 and 3, and between them player 1 wins means 3 is occurring infinitely often. It means this target vertices are occurring infinitely often. Okay. Now suppose I take a play which is good for player 1 in the Bushi condition. That means t is occurring infinitely often. Here clearly the max priority will be 3, everything else will be 2, right? So that's the point. As in, essentially we are saying that the Bushi objective can be seen as a special case of the parity objective with very small numbers. Okay. Good. So now comes the actual lecture 2. Okay. So we are going to look at 2 algorithms. So one will be a usual divide and conquer method, just like what we did for the Bushi case. We will do something, then we will run the algorithm on a smaller thing, then we will patch it.
In the last slide, what was the first question that you had given?
That I think we answered. What are the winning regions? We just already discussed that. So let us start with this 1, 2, 3 and 4 for the moment. Okay, so I have a graph, some of them are marked 1, some of them are marked 2, 3 or 4. Now the highest priority is 4. Okay. If the highest priority occurs infinitely often, in this case if 4 occurs infinitely often, it is good for player 0. Okay. So let us think of this highest priority as some kind of a target set of vertices, and let us see what all player 0 can do by winning by reaching. Can he win by reaching 4 infinitely often? This is the kind of question that we want to ask first. So let me first look at the set of vertices that have priority 4. Okay, these are all the good vertices. Now firstly, if I look at this reach 0 of P inverse 4, okay, these are the set of vertices where 0 can force the game to reach 4, only reachability so far, nothing else. Okay. Now I have a smaller game. Okay. In this smaller game there are priorities 1, 2, 3, not more than that. Okay. Let me look at this smaller game and solve it for the moment. Okay. And I will have winning regions in this smaller game. Okay. Now I want to kind of, it is not over yet. Now how do I patch things together is the question.
This reach 04 will forcefully make it to reach
4 ones, just 4 ones. Okay.
It can contain square or circle.
Anything, it is possible, it can be square, 0, anything is possible. So look at that question. If this were empty, okay, that means what? Even if the game comes here, 0 is winning anyway. Okay. Previously 0 was forcing it to go to 4. If the game comes here, 0 will again force to go there, but if the game comes here, 0 has a way of winning, because we know that in the smaller game 0 has, this is the winning region. Okay. So if W1 prime is empty, we know what to do. just everywhere 0 wins. Okay, that will be one base case. Otherwise, it is a question mark. Okay, let us see what happens otherwise.
What do you mean in terms of this W0? We are still talking about the parity game setup, right?
Parity game only, yes.
So what does it mean that 0 has a way of winning there? Like
Huh.
we can find what's the weakness?
It is a smaller game. There is a winning strategy in this smaller game. See, the point is 0 cannot go here.
So that's
Huh.
the smaller game, like it's an induced game within that region.
Yes.
So basically at that time, though, the rest of that thing does not exist.
Yeah, I will tell you what exactly does not exist. See, because 0 has everything here, okay, and 1 could potentially go here,
Yes.
but if it goes there, 1 is going to lose. So anyway, we are cutting this edge, and then looking
That's
at
why you don't have crossover. And then why is only 0 only going there? 0 has no reason to go to W1 prime and come
oh no, sorry, I just meant that 0 has no edge here. Okay, yes, 0 may have edges here, but it will not take it. Yes, okay. Are you with me, guys? Okay. So what was I saying? What if this W1 prime is not empty? Okay, so then we are again in this Bucci like situation. You see, like where we do not know what to do. Like it could very well be the case that my 1 comes here. So now we have to do something more. Okay, here there will be a second recursion actually. So what we are going to do is we are going to look at W1 prime, and then see this is good for player 1, okay, and so player 1 will try to come here, okay, and all of these vertices are already winning for player 1 even in the big game, right. Now we are left with part of the big game for which we do not know what to do, and let it be G double prime, okay, but it will be a smaller game. We do it recursively. So we call, I will repeat in case, so we call the solver on the smaller game, and then we ask what to do. Now I claim that it is over, okay. So I will tell you once again. So this is W1 prime coming from the first step, and 1 has a way to win starting from here, okay, and in all these vertices 1 has a way to force the game to come into this trap, and 1 will win there. Outside 1 cannot force the game here because otherwise it would be here, 1 has to be here only, and 0 if it comes here it will lose. So 0 will try to be here. So here is a small game which is kind of a trap, and here we know that these are the places where 0 can win and these are the places where 1 can win. So these are still going to be winning in the big game as well, because after patching up 1 anyway cannot go here, but if 0 comes here 1 has a way to win, okay. So in the big game all of them, these things will be winning for player 1 and this will be winning for player 0.
So if W1 dash and reach 1 W1 dash is not there, then W1 double dash 1 will still win there.
Come again? You mean this part?
If both W1 dash we remove it, reach 1 W1 dash we remove it, then W1 dash double dash will still win.
Yes, yes. If I start from here, 1 can somehow win by just staying inside.
Then why is it not in W1 dash?
Wait, see, the point is we are looking at, if I start with a vertex here, who will win? When you are here you can say why it is not in W1 dash, but I am saying like for a vertex in W1 dash and for a vertex here I need to know who is the winner, right?
So basically, how do we find W1 dash?
This one?
Yeah, the first W1 dash. How are we finding it?
It's the
recursive
step.
So basically, we find the first cycle where W1 wins. Then we find the reach W1. Is that how it?
I will
there are
show you the
multiple
algorithm.
cycles.
Now that you get a feeling of what is going on, it's time to show the algorithm. Oops. Oh, sorry. I so I will run you through the algorithm. Yes.
So this bottom square, that is the entire graph.
Yes.
So it includes W0 prime also.
Yes. 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 Yes.
This is what W1, the small circle on the right side.
Yeah. This one.
W1 bottom right.
W1 double prime. Yes. So this is a small game, smaller game, and this is the winning region of player 1 in that smaller game. Okay. So maybe is it here? Right. See, there are two recursions. Okay. In the first recursion, we compute this and this. Okay, it's the same thing but with color now. Okay, and before getting into the second recursion, we know that we can actually fix these vertices to be winning for player 1, but for the others we do not know, because from here we do not know what happens. Okay, is that yes, correct, because player 1 sorry, it should be here. Did I make it oh, I'm sorry, you see this should have been, I messed up the I do not know if it makes a difference, but see, because it was that should have that, see, because it is 0, so 0 should go to where 0 wins. Maybe this must have confused some people. I will repeat. Okay, yeah, so we will do this n number of times, don't worry, but so this is the big game. Okay, once again, and these are very good vertices for 0. Okay, and here these are the places from where 0 can go to this big vertex. Now here is a sub game where 0 cannot go like that. 0 is restricted to be here. Okay, and in this sub game, these are the winning regions for 0 and 1. Okay. Now as long as from here I am able to jump here, it is okay for 0. I just pointed it at 1 there, but it should have been 0. Okay, because from here, from 4 I can go to 0 and win. Okay, so I am actually looking for reach 0 of W0 prime. Okay, this part is, you can fix that these are all winning for 0. Now we are undecided about this part, and we run the second recursion there.
We know that has that P inverse 4 part inside, right? And that is very good for
Yes.
one.
Yes, it may have some P inverse 4. See, some of the P inverse 4 may come here, some of them may stay back here.
Why did they move to there?
If you have a, so for instance, if I had an edge, see, for example, if I had 0 pointing here, okay, but it may not be the case also, in which case we do not know, because there are some P inverse 4 edges where you may not be able to do a cycle again.
Yeah, there is what is it? You reach once, but that's it.
That's it, yes. Okay, so that's why we will have to do the recursion a second time here.
In this we have just removed the red region. You have
Yes.
written G minus reach 0, V0.
Yes, we have removed, we have only fixed the blue region. That is the only place where we have a decision at the moment. Initially we had no clue about any vertex. Now after the first recursion, we have decided that the blue region is winning for player 0.
And red also, right?
No, not yet.
Like red, we removed red region. No, not red, the reach 0, W0 dash.
Yes, the purple one, the reach 0 W0 prime is also winning for player 0 now.
And so the reach 0 P inverse 4, that is still there in the game or?
It's spread. Some of them could have come here, some of them could have been here.
Okay. Because after reaching P inverse, we don't know whether it will go to 1 or not.
Yeah.
So we have still included.
Yeah, these are the, some of them could already be here. So we are only strengthening our decisions, you see. At this point we have strengthened the decision up to here. And then we do a one more recursive call, and then we are done actually. After we do a recursive call, my claim is that this part is winning for 1 and the rest of them are winning for player 0. Okay, that is what I meant. I will give you a little bit of time to think about it, and if you have any questions you can ask me later. Okay, so here is actually the, I mean I will just quickly go through this pseudocode, which is essentially the same thing, but because it will help us figure out the running time also. So we are looking at, by the way, in general D could be odd or even, right. So in which case you just take, if it was like say 5, then we should have done the same thing at the perspective of player 1. You see the highest priority, we look at its parity, and that particular person is interested in going there, right. So if j is d mod 2, let I be the other player, okay. It is like 1 minus j symbolic, like, okay, right. So first what do? We look at reach j of p inverse d, okay. You see that is what we look at, and if already that is like the entire set of vertices, we just stop, we just conclude the j wins everywhere, otherwise we go to this else part, okay. So here there is a smaller game G prime, that is this game, okay, and in G prime we run it recursively, okay. Now if this part is empty, that is what this says, if Wi, then once again we conclude 0 wins everywhere, I mean j wins everywhere, 0 is j, 1 is I essentially, okay. Otherwise what we do is, we are here, right, we keep Wj prime, and sorry, what did I do? I should have sorry, it should be j, okay. I keep Wj prime and this is Wj prime, compute reach j of Wj prime, look at the smaller game G double prime, okay, run it once again, okay, run it like this, and I get some answers, okay. And here I should just make it sorry, voila, yeah, okay. I mean, yeah, enough, I think enough is, was there a question? No, okay. So this is the idea. So I think the main point that you need to, I mean I would like to kind of pass on is that there are 2 recursive steps on smaller graphs. So how does that work with the running time? So if I have n vertices, each recursive step takes t n minus 1 at most, okay. This is a very naive runtime analysis, you can do a little bit more careful, and in each step we are doing some reachability computations that can be done in OM, right. So what do we have? We have t n is less than 2 times t n minus 1 plus OM, and that is already a problem, because the running time of this is 2 power n, because there will be 2 power n times you will call the algorithm, okay. So this gives you an exponential complexity, okay. So this is the classic algorithm for parity games, and it gives an exponential complexity. Recently 2019, this very same algorithm with a small modification was brought to quasi polynomial. So when I say quasi polynomial, you want the running time to be n power log d, where d is the number of priorities, n is the number of vertices, essentially n power log n. See, currently this is here n is in the exponent, okay. In fact, yeah, this will be this you can even bring it to n power d actually by some sufficient runtime analysis. You can see that this will be roughly n power d, and then you have to bring it to n power log d. Okay, so that's a very significant step. You can read this paper if you are interested. Okay, very good. So shall I move on?
After first breakthrough came at 2017.
Yes, yes.
Then someone figured out to make the earlier one positive.
Yes, correct. So the actual algorithm, which was the first 2017 algorithm, it did not use this method at all. Okay, but then later people figured that every existing method can be made quasi polynomial. I mean, in some sense, that's what happened more or less. Okay, should I go over this fact parity is in? So, have you guys seen what NP, co-NP, these kind of things? Is it maybe it should is NP co-NP expected to not really no, yeah, that's what. So let me just make a.
Why don't you raise hand? How many of you know?
How many of you know NP co-NP? Okay.
ONP is complete NP, right?
Complement of n.
Complement, yeah. Okay, so
The expectation was discrete match, some basic probability.
yeah. Yes, yes, absolutely fine. There is no need for you to know this, and if I'll just make a remark for those of you who have already who know this. So, what is the question? The decision problem is given parity game G, vertex V, is V winning for player 0? This is the decision problem. Okay, why is it in NP? By the way, so I did not do this part. You can see that you can also compute a memoryless strategy. If you are winning, you do not need any, I mean, once again the positional strategy that we talked about will work already. Okay, in the sense you can, from the algorithm you can extract a positional winning strategy. So, why this is in NP is you need to guess the strategy, okay, and after guessing the strategy you are left with a graph with priorities, in which you have to check that in every cycle the maximum priority is, no, in the sense, yes, in every cycle is the maximum priority even. This is what you have to check. This is every cycle, like, I mean, not just, and this you can actually do it in polynomial time. Okay. First of all, you look at cycles, you first look at cycles. Okay, you remove the vertices with the highest priority and still see if the max priority is even, then remove vertices with that priority and see and so on. So, you can do it hierarchically. Okay. The fact is, the point is that it can be shown to be in NP. Now, why is it in co-NP? What is the complement of this problem? Is V winning for player 1? Okay. Yeah, you can do the same thing, you guess a strategy for player 1 and do the same thing. So, that is why it is also in co-NP. Okay, fine. So, that is why it is in NP intersection co-NP, does not matter. Okay, good. Yes, now let us come to another completely different style algorithm, no divide and conquer at all. Okay. So, I will, so the point is people have attacked parity games through multiple angles through completely different looking algorithms. So, this one has a absolutely different flavor, there will be no search, no DFS, no BFS, nothing. Okay. Let us see. So, here is a meta statement. I will try to explain what it means as I go along. So, what we want to do is we want to attach something to every vertex, that something is some quantity. I will explain what that quantity is, so that if the quantities locally satisfy, as in for all its neighbors the quantities satisfy something, you will check a local property. If at every vertex some local property is satisfied, something nice happens. Okay, that is the spirit of this algorithm. I want to do something locally so that in the whole graph put together it is good for me. I will explain this key idea through in steps. Okay. So, let us first look at a very simple property, which is like I give you a cycle, just a cycle of vertices V0, V1, V2, V3 back to V0 with priorities. I want to know whether the max priority is even. Of course, it is not a very big deal, you just run through it. okay, but that is not the point. I want to illustrate this meta idea, what that is. Okay. So, in fact, so I will write, so here is your exercise. Okay. So, here are 2 cycles. Okay. In this cycle I have 1 1 2 1 2. What is the maximum priority in this cycle? 2. So, I will call it an even loop. This is 1 1 1 1 1. What is this? It is an odd loop. Okay. Now, here is an exercise. I want to associate a natural number to every vertex, okay, and that natural number should satisfy certain properties. Okay. So, the natural number I will call it, I believe this is zeta, okay, zeta 1 of Vi. Whenever I am having 1, the quantity here should strictly decrease. Okay. Whenever I am at 2, I have no constraints. Okay. So, try to give natural numbers. You can start with 0 if you want, and then see how it starts to work. Is the question reasonably clear? I want to, so for instance, if I associate value, let us say 3 to this vertex just for some reason, then here it has to be 2 or less, it cannot be 3. You see? Can you do this exercise for both the graphs, for this graph as well as this graph? So, any answers? Tipro? Yeah.
So like I'm talking about the odd loop, like no such assignment is possible.
Yes, correct. In the odd case, you cannot make such an assignment, but here you can. You should be able to make an assignment. So, here the problem is, no matter whatever number you give, suppose you gave 100, okay, oops, this one has to be smaller than that, this, so this is smaller than 100, this is also smaller than 100, smaller than 100, smaller, smaller, but this is 100, here you cannot decrease further. Okay. You see, this is a mechanism which is identifying loops that are odd, okay. Whereas here you will be able to give some appropriate numbers which gets reset at 2, like for instance I can give yeah, let us say 3 2, I can just give 0 here, okay, and then here I do not care because there are no constraints. I can once again give say 1,
So I can give 0 there.
you can give 0 there, yeah.
But it's natural number.
Oh well, give 1 here, okay. So, no, anything, I do not think.
Okay, we don't have a rule per se what happened there. Any number can be given.
Yeah, any number can be given, okay, very.
But it should be less than 2, right?
But it should be less than 2, yes.
It should be less than this 2, yes, correct, you are right.
Okay, so 1 is the one.
1 is a possibility, okay, and then here you can again start with 1.
No. 3. We have to decrease it first.
2.
No, right here there is no need.
No, after 1. No, after 1 we have to.
This is 1 and here you can put 0, right, and here there is no need, no, there is no constraint. You see, so when I am walking along a loop, I need the ability to reset my values which are decreasing, so that it means I am seeing a higher priority.
It doesn't matter, but each vertex has a natural number only associated.
Yeah, let's start with yeah, okay, because you will see what it means, okay. Okay, before I go into this, so the point is, you should think of it as like this: if at all I see a 1, I should see a 2. That is what this means, right? So that is what this is. So now let us like develop this idea a little bit further. When I have 1 2 3 4, okay, here, okay, what is it an even loop or an odd loop? Odd loop, because the max priority is 3. This one is an even loop, okay. So here it is not enough for whatever we did with one quantity. So the idea is, if I see a 1, I should see 2 or something bigger, 4. If I see a 3, I should see a 4, right. So I will associate 2 quantities, one denoting the constraint for 3 and one of them denoting the constraint for 1. Okay. So, here is the,
can see 3 also.
come again, sorry.
You can see 3.
Yeah, you can do that, you can say that, but because since we are also saying that if you see 3 you should also see a 4, so you do not have to, it gets subsumed, like, yeah. See, that is what this is telling you. So, if at all you see a vertex, so I am going to associate 2 quantities, one number here, one number here, to every vertex, and here are the constraints. At priority 1 vertices, this quantity should strictly decrease. Okay, this was a number as before. Whereas the other one, you just maintain it, because just by seeing 1, the constraint is not, you cannot nullify the constraint yet, you need to see a 4. So, if you see a 2, you get rid of the constraint on 1, no constraint, but preserve the constraint on 3. Okay, that is what this means. If you see a 3, no constraint on 1, but strictly decrease on 3. Okay. And if you see a 4, absolutely no constraint, everything can be nullified, like a hierarchical way of associating constraints. My claim is that if you are able to fit a measure like this, then the loop should be even, okay, even if you have 1, 2, 3, 4. So, that is why.
First line should it be eta 3 b I plus 1? First line.
Oh, you are right, yeah.
Second one, it should be 4.
Actually for everywhere this should be here also. Good, and here, yeah, correct, you are right. Okay,
So can you once again explain the first
this
thing?
should be,
If we are on Vi, like if Vi is 1, then we say that the 1 in front of 1 should always decrease.
correct.
And in that loop only, the thing in front of 3 should be equal or greater, like.
Yeah, so here is my suggestion. Okay, let's try this example. I suggest you just put 0 0 first to everything. Okay, just try with putting 0 0 on both places for everything. So, this is zeta 3 and this is zeta 1
We are giving 2 numbers
to each. Now, they do not satisfy the constraints immediately. Okay, so for instance, if I take this one, okay, this is zeta 1, right? This is zeta 1 of its successor. There is no strict decrease, right? Can you keep increasing the numbers so that finally you end up here? At every local every vertex, a local property should be satisfied. So, can you try this? I think it is useful to try on both of them.
It wouldn't be possible on an odd loop, right?
Yeah, correct. So, on the left hand side it should not be possible, you will have the need to go on increasing and it will never stop. Yes, correct, exactly. On the right hand side you should be able to actually associate, okay, you should be able to give some numbers.
in this odd cycle, so whatever will be the highest odd number, only that should follow this, that it should decrease, keep on decreasing. The epsilon.
Correct, in some sense.
And
Right.
rest all we can give no constraint as we go on.
Yeah, right. I
That
understand.
is what I was asking. Like if on one of the 4 conditions of the 3 conditions is changed, then also we can have a similar situation.
Correct,
Only one
correct.
is one
Yes.
of these 4 conditions is such that is making this.
Correct. Right. You are right. Yeah, it's the kind of the highest odd number will be a witness for not satisfying this constraint. You are right. Okay. So maybe I can just do it here, just in. So essentially, this is called the lifting algorithm. Okay. Okay, fine. So we will. I'm just going. I'll do it on this graph because it's a nice behaving graph. Oh wait, no. It is this one, the one with the 4. Okay. So I will put 0, 0 first. Okay, I will start like this and I will arbitrarily pick a vertex and see if it is satisfying the constraint or not. So let me arbitrarily pick, let's say, this one. Okay, is it satisfying the constraints? Here, yes, because you see for 2 there were no constraints. As long as this was lesser than or equal to, it is okay. The strict less than was not imposed. Okay, fine. Then I am going to take another vertex. Let me take 1. Okay, this one should be strictly bigger than this. So what I am going to do is I am going to cut this and then make it 0, 1. Okay, then I pick something else. Let's say maybe I pick.
Isn't it always better to pick a 1 as long as it exists in the graph?
Yeah, the order in which we pick, it's not clear to me. Okay, but there is a theorem which says that I may not. In the end, you will reach the same values, no matter in what. Yeah, so that's right. So in no matter whatever order you pick, you will reach a fixed point, which is a unique fixed point actually. Okay,
So I was just saying start with 1 because 1 has a constraint. Therefore, both zeta 1
Yes.
and zeta 2. So you want to satisfy the constraint and ensure other things don't
Yes.
violate those constraints.
no, I agree with you. Yeah, that's that's a natural thought, but it seems like it doesn't matter. So anyway, so I mean, like, maybe I'll just do one more and then we will, let's say this one. Here I need to kind of put 1 here and 0 here, right? And so on.
What was the zeta condition there? Was it strict?
If it is this, at this point it should be strict.
Which is priority 3.
Yes.
It should be higher than
In
its
its,
vi%.
yes.
The constraint was on epsilon 3, right?
Yes, so that's right. So this one is this is zeta 3,
Okay,
this
first
is
zero.
zeta 1. Sorry, yeah. Okay. I can continue, but it will take some time. But I hope you get the point. So I think you can just keep lifting the values. The point is that here actually it will be helpful to illustrate. What happens is you do one round and then you get a bigger number. You start with something like 0, 0 and then you end up with 1, 0. And then once again you will end up with 2, 0 and stuff like that. So you will have to go on and on and on increasing. So there will be no possibility. Okay. So you see the fact that it is an even loop can be recognized just by associating some suitable quantities and satisfying some local properties. Okay. So these kind of measures, these quantities are called progress measures in the literature. Okay. So I kind of simplified it slightly. There is one more point. I will see if I can. So you don't have to do it independently. Let me come to this. So what we are going to do is we are going to associate tuples to every vertex, right? So if there are d priorities, now here I have assumed that d is even. Okay, just for simplicity, it doesn't matter. Okay. So then you look at d minus 1, d minus 3. For each of the odd values, you have a kind of a quantity, okay, and there are tuples. We are going to look at lexicographic ordering among the tuples. Okay, you will see that. So what does it mean to say lexicographic ordering? So here is a tuple, here is a tuple. This is 4, this is 4. This is 3, this is 2. So this is bigger than this. So lexicographically, this is bigger. Okay, that's the usual dictionary ordering. And then what is and then we have a function which maps every vertex to one such tuple. Okay, and there is one more notation which is like if I want to look at a sub part of the, in the sense like I want to start the tuple, what do you say? What is this called? I want to look at a part of the tuple starting from some point. Okay, so if I have k, okay, if k is odd, there will be an entry for k, right? Zeta k. I will look from k and everything to its left. Okay. Whereas if k is even, I will look at k plus 1 and everything to its left. That is what this notation means. Okay. I am just formalizing the ideas that we discussed so far. So for instance, if my zeta v is this, so this is like for priority 1, 3, 5, 7, 9, 11. Okay, and if I look at zeta 3, I just start from this tuple and I take everything to the left. That is zeta 3. If I look at zeta 4, I look at the next big number and I start everything from here. That is what gives me this. Okay, these are notations. Now the question is, given a graph and such a function, when do we call it to be a progress measure? Okay, when is it actually measuring progress in some sense? This is this says, I will try to put it in pictures. What this says is that at every vertex v, okay, you look at all its successors. Okay, see, this will have a p of v, a priority. Okay, I look at the tuple zeta v restricted to p of v, and that tuple should be smaller than the corresponding tuple for each of its successors. Okay, I look at, see, I looked at the part of the tuple corresponding to the priority. I do the same for everything else. Okay, and this should be bigger than or equal to, and if this p of v is odd, it should be strictly bigger than or equal to. Okay, sorry, once again, like I am associating values, and for each vertex v, I look at the part of the tuple that corresponds to this vertex. I look at each of its successors, and I still restrict it to the part corresponding to p of v only. Okay, and this value should be like this, bigger than or equal to, and if p of v is odd, it should be strictly smaller. Okay, if I am able to associate a progress measure of this kind, then the claim is that all cycles in that graph are even. In the sense, the maximum priority in any cycle is going to be even. That is what this this will imply. I mean, that's a lemma we can. So, for instance, is this a graph in which all cycles are even? No. 1, 3. You see, so here we should not be able to admit a progress measure, but if I just move this to like 2 or something, then we should be able to fit a progress measure. Okay. So here is one side, then there is the other side, okay, which is much more important. Yes.
How do I know that I will not be able to fit a progress measure? Like, do I try to adjust the value?
Wait for the next lemma. Okay. So you are right and absolutely right. So here is where this thing comes. Okay. If at all there is a progress measure, there will be a small progress measure. The values will not be more than the number of vertices in the graph. Okay. So if you go beyond a certain value, you can just say give up. There is a problem. Okay. That is what this means. So here is the theorem. A graph G has all cycle. We are so far in the level of graphs, not games. Okay. It is a graph theoretic question. I have a graph and in which every vertex has some priority. My question is, are all cycles even? And for this, here is a theorem which says that a graph has all cycles even if and only if it admits a small progress measure. Okay. Very good. And of course, this can be extended to this can be made into an algorithm. Okay. Just by whatever we did, start with 0 everywhere, pick an arbitrary vertex, lift it to the next immediate tuple which makes the condition satisfied, lift it to the, keep picking this, find a vertex which is not satisfying the constraint, lift it till it satisfies the constraint, lift it till it satisfies the constraint in the least possible way, and in the end, if you go beyond a certain bound, just say that this is not helpful. Okay. So it turns out, I am not going to, this is the main idea, key idea, this is what I wanted to. It turns out that you can extend this thing to the parity game setting, in the game setting also, if you have both player 0 and player 1. Okay. Roughly what happens is, here you have max, right. For one of the players you will use min, and for the other players you will use max. Okay, it is like some kind of a min max kind of. Okay. And once again the same kind of lifting algorithm, and you see the running time of this is see there are how many d by 2, the tuples are of size d by 2, where d is, and each of them can go up to n the values, and you can actually lift it one by one also. So, there is a lower bound. So, there is they manufactured a graph for which you will lift it till this point. Yeah, it is very tight, it is tight, yes. So, it is n power d by 2. Okay, this is called the progress measures algorithm, and its running time is once again quite high, and once again like after we knew that there was a quasi polynomial algorithm, the same, I mean Marchin was involved in this progress measures. They also managed to show that you can encode these tuples in a succinct way. Okay, so, there are exponentially many tuples. Somehow they came up with a very clever encoding of these tuples, so that you just do lifting on these encoded domain, you will achieve whatever you want. Okay, that is what is called succinct progress measures.
Does that give a faster algorithm?
And it gives quasi polynomial n power log d. Okay, it gives, yes. Okay, so they somehow it is like, see, finally everything boils down to doing a binary encoding, but of course how to do it is the important. This was a very, I mean I found it very non-trivial way to encode this this domain of progress measures. Okay, so I think this is a good point to stop. Okay, so we saw what parity games are, and we saw two algorithms. So I think this is good to digest here. Then let's take a, we can take a break. Yeah, we can take a, yes. Let's take a break now, and then I will try to give the key ideas behind one quasi polynomial time algorithm. So, because so far I have given you only exponential time algorithms, let us try to understand one of the quasi polynomial, not all the details, just the high level view. Okay. Thank you.